Welcome. In this lecture I'll cover tearing modes, and these are a kind of instability which can occur when the plasma has a finite resistivity. And so when there's resistance or resistivity in the plasma, the magnetic field can diffuse and is no longer frozen into the plasma. This is linked to, in tokamaks, there's a threshold where the tearing modes can become unstable. It's called the tearing stability index, gives a way of calculating this. And this is linked to a Rutherford equation, which is the time evolution of the size of an island. And so it determines when an island grows, when it shrinks, and what amplitude it saturates at. So this appears quite a lot in studies of tearing modes. So in ideal MHD, it can be shown that the field is essentially frozen to the plasma. And so as the plasma moves around, the field is moving around with it. And this only happens when there's a zero resistivity. We've come across the induction equation for the ideal MHD, and now this becomes a little bit more complicated when you have resistivity, because your electric field, U is the fluid velocity, and now instead of zero here for ideal MHD, we now have resistivity times a current density, J, so eta here is resistivity, and it has units of ohm meters in SI units. If you now put this into the equation for the magnetic field, so you have dB by dt is minus curl of E. And just substituting this into here, in ideal MHD this became curl of U cross B. Now it becomes curl of U cross B, which is the ideal MHD part, plus an extra bit, which is this curl of E to J. And so this is the new part from resistive MHD. We now use a vector identity, so we have the curl of a field A is the divergence of the gradient of the divergence and the Laplacian of A. And now we can use this formula and expand this out. It's easiest if, for now at least, eta, the resistivity is a constant. So if you say eta is constant, this simplifies things, because the divergence of J is zero. There's no current or charge buildup anywhere. So we have the divergence of J is zero, and so we can just turn this into. So we have the term from the first part, which is the curl of U cross B. So a term here which is like the curl of, here I have eta, then J is 1 of mu naught curl B, so this is like 1 of mu naught curl of B. And so if this is constant, so if eta is constant and mu is constant, that just comes outside. So this becomes an eta over mu naught, and then we have a gradient of divergence of J, which is just 0, and Laplacian of J. And Laplacian of B. And so if divergence of J is 0, then this term just looks like a diffusion. So we have, if I write this out now, this is dB by dt is the part from ideal MHD, plus this term here, which is eta over mu naught del squared B. So it's Laplacian of B. And this is just a diffusion equation. So we have a dB by dt on the left, and the second derivative in x on the right. And this represents diffusion of the magnetic field through the plasma, with a coefficient eta over mu naught. So eta over mu naught must have units of like meters squared per second. So it's like a diffusion coefficient. And we can work out roughly what that is. So we can assume we have a collisional plasma. So we can use Spitzer resistivity. And this depends on the charge of the ions, Z. So here just assume 1 for hydrogen, log lambda, which is usually around 10 to 20, that kind of area. And this is temperature, electron temperature in EV, as to the power of 3 over 2. So as the plasma gets hotter, the resistivity drops. And so for TE is about 1 keV. So that's like a core of a large plasma, large tokamak like jet or so. My log lambda is around 15 or so, and z around 1. So this gives eta of order 10 to the minus 8 ohm meters. And so eta over mu naught is of order 2 times 10 to the minus 2. So meters squared per second. This is usually quite small. This is much smaller than the typical kind of heat or particle diffusion, but it can become important on small scales because the equation is a diffusion equation. It depends on, here in this part at the top, this is a second derivative in space, and so if you have very small layers, then we have 1 divided by the small number squared, and then this can become large, because essentially we can say that so del squared is roughly 1 over some kind of length squared, so of order, and d by dt is of order 1 over a time scale, and so we can say that 1 over some kind of time scale is roughly eta over mu naught 1 over length squared, and so the time scale for diffusion to occur for some kind of reconnection, as we'll see, is roughly L squared mu naught over eta, and if you have very small layers, so thin layers or a thin current sheet, so if you might have L is about 1 millimeter or so, so it's getting down to iron lambda radius kind of scales, then tau can become a few tens of microseconds. So this gets to get about 50 microseconds, which is kind of on the time scale of instabilities to occur. So you can, if you get very thin layers of currents, you can make have instabilities or changes in magnetic field on a short time scale, but it requires very short length scales. So if you make this 1 meter, for example, like the size of the plasma, then this would be 50 seconds rather than 50 microseconds. And so the time scale for the magnetic field to diffuse into the whole plasma, so for L is around 1 meter, tau is around 50 seconds. So magnetic field or current diffuse into the plasma on very long timescales, but very short timescales if there are very small structures. And so what this looks like if we have some simple models. So a common model for a reconnecting or some kind of tearing mode is you have a current sheet. So you have a very thin layer of current. Try and draw this like this. So you have a thin layer of current. So this is a very small length L, and this is produce a magnetic field which has a shear, so has a jump. So we produce magnetic fields like this. So it's kind of reversing sign. You often see this in different forms, but it might have essentially a reversing magnetic field. And what happens if this is unstable is essentially this current sheet breaks up into pieces. So rather than having one long current sheet, and this is J, so it instead breaks up into pieces like this. And we end up with a magnetic field which, instead of being uniform like this, now actually looks more like this. So we still have a magnetic field up here going like this, and reverse its sign over here. But now what's happening is that the field is doing this. So we form these X points here and O points in the middle. So you have magnetic fields which form kind of O points here. And these are called magnetic islands. So this is a current filamentation. So you have a sheet of current and it breaks up into pieces. And this corresponds to changing of topology of the magnetic field. So the magnetic field started here as just straight, so it might be nested flux surfaces, for example. And now we have this kind of island structure. And this is a different topology to this. And so this is forbidden in ideal MHD, but finite resistivity can allow this to happen. And it happens when these length scales are short. So if L is small, then this diffusion of the magnetic field can occur on a short time scale. This kind of situation can happen in a tokamak. So if you remember the cylindrical Tering mode equation, so this described what happened when you had a perturbation to the poloidal flux. So the flux surfaces has a kind of ripple perturbation to them, and what happened to the perturbed current density. And so this has a singularity when Q equals m over n, and this corresponds to a very narrow current sheet. So in some perturbations, the plasma can become unstable and produce very narrow layers. In ideal MHD, this is an infinitely thin but infinitely large current density. Of course, the total current is finite, but it's just squeezed into an infinitely thin layer. If there's any kind of resistivity in the plasma, then this layer has a finite thickness, and then this layer can become unstable like this and break into islands. And so at these layers, resonant layers where Q equals m over n, we can get Tering modes. So in a torus, or might be easiest to draw in a cylinder, what happens is you have this. I'll try in a torus. So we have nested flux surfaces. So in equilibrium, it just looks like a whole bunch of nested surfaces. One of these surfaces, say, has Q equals m over n, and usually this is either Q equals 2 surface, for example, so it's two ones. So Q equals 2 over 1, or occasionally 3 over 2, but 2 ones are usually the most unstable. What can happen is at this surface, it goes from magnetic fields being kind of a nested flux surface like this to filamentation, so the current filaments, and you end up with kind of islands like so. So it ends up breaking into a set of islands. So this has got a 4, m equals 4 accidentally, but the idea is there's a whole bunch of islands forming here, and these islands are following the magnetic field. So it's now this surface here is now kind of broken up into island chains, and now the particles of heat can move from one side of the island to the other, and so these islands do not confine the plasma as effectively as the nested flux surfaces, and so this degrades the confinement. Now the stability of these Tering modes is determined by something called the Tering stability index, and it's actually related to this current sheet. So this current here gives a jump in delta psi from one side of the island to the other, and that in turn can be related to the delta W equation, and so it's called, so delta prime is this Tering stability index, and it's essentially the size of the current sheet produced at the surface, and this you can write as the jump. So I'll use this double brackets to mean the jump in 1 over delta psi, and then we have a d delta psi by dr. And so it's the change in this from one side of the island to the other, and it's related to the current perturbation, so delta J on the surface, and in turn can be related to the delta W, so the energy lost by the plasma when this instability occurs, and it's unstable if delta prime is bigger than 0. Okay, finally we can use this delta prime then to work out how the plasma will behave, how the Tering mode will evolve, and the equation for how this the equation which determines how the plasma Tering mode evolves is the Rutherford equation, which was developed in 1973, published in 1973, and this has been developed and added to over the years. So add more and more effects to this. So you can add bootstrap currents and polarization currents and other stabilizing effects to it as well. But here we'll just look at the simple form. So the idea is that you have an island structure like this. So the island So here we have magnetic fields which are forming these kind of surfaces here. So we have O points and X points, more O points here. And then characterize this as the width of these islands. So this width here is W. And then what we say is that the growth of this island is related to the diffusion of current. So it's current that's diffusing, which is causing islands to grow. And so the radial magnetic field. So if you imagine that this was the starting, there was some flux surface here, which has been torn into islands. At this point here, there's a BR. At this point here, so the magnetic field now has a radial component, and that radial component evolves in time. And so we just say that the evolution of the radial component is termed by the diffusion equation. So this is what's limiting the growth. And then imagine initially these islands are very thin, so they start out zero size and they grow. But if they're very thin, then the gradient along the theta direction, so this is like the theta direction, then R is outwards here. So the derivatives in theta are small, derivatives in toroidal angle are small, and so this is approximately just the derivative in radius. Now if this is a perturbation to the poloidal flux, then we have that delta B R is just minus 1 over R d psi, or d delta psi by d theta. And if we assume a sinusoidal variation, so we just say that delta psi is like some radial function times e to the I m theta as n phi, so that's kind of sinusoidal perturbation. Then this d by d theta just becomes an im. Okay, then we're going to do a simple calculation here, so I'm not going to go through the full derivation because it takes a very long time. So here we'll just look at a more heuristic calculation. So what we're going to do is we're going to integrate this equation from one side down into the other. So we're going to calculate the integral from minus w over 2, so from this side, to plus w over 2. So we're going to from one side to the other. And first we're going to integrate the dr by dt, integrating this in R. And this, of course, is just the integral of the other side. Now this on the right side, so if we assume eta is constant, this whole thing is constant, and so it's just the integral of the second derivative, which is just the jump in the value. So this is just eta and mu naught come outside, and then we just have a d delta b r, and the gradient, the difference between the gradient from one side to the other, so plus w over 2, and this is just the jump across the island. And then on the left hand side we just assume that delta br is approximately constant, and so this whole thing is roughly w times delta br by dt. And then we just write that the size of the island is related to the radial magnetic field. In fact, we can work out that the perturbed magnetic field in the radial direction is proportional to the width of the island squared. It makes sense that it should be at least increasing, because if you have zero radial magnetic field, then there's no island. As the size of this island is increased, the radial component here must increase. And it turns out it's related like this. And so you can turn this into a d by dt of the width, and so you end up with dw by dt. You bring essentially some of these w's over to the other side, and you end up with eta mu naught, and again this jump term here. And you can absorb one of the w's into this delta psi, and this is just eta over 2 mu naught times the tearing stability index. And so if delta prime is bigger than 0, then dw by dt grows. W by dt is greater than 0, and the magnetic field, magnetic island grows. If delta prime is less than 0, then it shrinks. In real talkback, you have neoclassical effects as well. So there's a breach-lock current term which is added onto this, which tends to drive magnetic islands unstable.